Hey everyone, in this video we're going to look at using the Dplyr package for data transformations and data manipulations in R. So just like usual, we'll complete this using R Markdown. We'll go ahead and get started. So the Dplyr package, which we've already seen some in previous videos, is very useful for operations working with our data, and very generally what we'd refer to as data cleaning. So often when we get data in class, it comes in this, be it in this class or other classes you'd take, it comes in this really nice, often ready to use form. Sometimes you might need to do one or two small things to get the data ready for a visualization or to fit a model. But for the most part, it's it comes very nice to play with, to work with. Unfortunately, in a real job, in an industry setting or a research setting, it's often the case that you get data that is not ready for analysis right off the bat. So stuff that's very difficult to work with. You may have like an Excel file. I think lots of statisticians have encountered this. You get an Excel file where like color encodes a variable in the data set. So maybe like if the cell in the Excel file is teal, that means this value. And if it's a red colored cell, it means this other value. And then another common difficulty in data sets is having lots of information encoded in the cells themselves. So like maybe the first 5 rows of the Excel file have header information about the data set itself. And then maybe there's more information interwoven in rows scattered or interwoven throughout the Excel file. So you don't have this nice, tidy set of observations or rows and variables. It can be in not so nice to work with formats that are difficult to deal with. So this data that we encounter in the wild, we need to clean it up ourselves. And Dplyr, the developers of Dplyr, have recognized this as a big time-consuming thing for statisticians and data scientists, and so have created this wonderful set of tools to simplify this process and to make it a little bit easier when programming in R. So we'll be looking at some of the fundamental functions in this video here, some of which you may already be familiar with, but we'll explore how we can use them and customize them to do some slightly new things. So the first function is the filter function, which is useful for picking a certain set of rows or observations from the data set based on a criteria. So a logical condition that we'll decide, typically based on a variable, determines if we retain these rows in our data set or not. So it allows us to filter out rows that we want to keep. We'll also look at the arrange function, which keeps all of the rows in the data set, but rearranges them or sorts them based on commonly a value of a variable. So you've likely done this before in Excel, where you can sort the spreadsheet based on a particular column. That's essentially what the arrange function does for us here. The select function works on the column level, or it manipulates variables or columns in the data set rather than observations. So it's sort of like filter and arrange combined, except for columns. So select can remove particular columns from the data set, and it can also rearrange columns in your data set. So it's a very useful function, one that you'll find yourself using often when working with data. The mutate function allows us to create new variables or columns in our data set that either can be entirely new or they can be functions of existing columns. Additionally, you can modify, you can keep columns that are already in your data set, but modify them slightly. Maybe you have a proportion, which is the decimal form of a percentage, but you want to change it to be the percentage form. So maybe instead of saying 1.00, you want the column to say 100%. We can do that with mutate. And lastly, some of the more useful functions in Dplyr, these last two are quite useful as well. The group by function and the summarize function. So these are very useful for calculating summary statistics or conducting very generally any types of operations on the data for different subgroups. So at the subgroup level. So for example, maybe you want to calculate a sample mean, but you want to do it across 10 different subgroups of the data. Or maybe you want to get the 5 highest values of a variable for each of 3 different subgroups. Maybe you want, for example, from the Palmer penguins data, you could get the 3 heaviest penguins from each of the 3 penguin species. We could do that with group by and summarize. So those are the useful functions that we'll be going over in this video here. But to start, talking again a little bit more about the Dplyr package very generally. So Dplyr is named because it's like a set of tools or a plier, which is a type of tool that we can use to work with data. So the D is for data, and then plier because it's like a tool for working with data. So very generally, Dplyr is useful for when we want to transform our data, which is referring to the process of creating new variables, potentially summary statistics based on groups in our data, or even altering existing columns in our data set. That's all referred to as transforming our data. Sounds a little bit fancy. Then manipulating data, we would say this is, some examples of manipulating our data would be renaming columns or variables, arranging the rows, rearranging those or observations, and also filtering out or subsetting particular observations or variables in our data set. So data visualization is not a part of the Dplyr package, although commonly you will use Dplyr to get your data in a form that's ready for visualization. But both are key skills for working with data sets, being able to clean them up and being able to visualize data. Data visualization is that's taken care of by the Ggplot 2 package, whereas Dplyr is for data cleaning. So although this isn't the most exciting aspect of working with data, cleaning it up and getting it ready for analysis, it's often what you spend most of your time doing. It's most time consuming, and unfortunately is a necessary part of data analysis and data science. That being said, even though it's not as exciting as fitting a complicated, say, neural network model or a random forest model, you can dramatically improve predictive modeling performance or the effectiveness of your data visualizations through proper and effective data cleaning. So it can be the case that by creating new variables in your data set using, say, mutate in a clever way, a simpler model, such as a linear regression, can outperform much more complicated models if you're clever about your data cleaning and transforming data wrangling process. Okay, so these are important and sort of overlooked skills sometimes because they're not the most fun, but it can improve your analysis skills in a lot of ways. So let's look at this real data set here on Michigan flights. So flights out of the 4 major airports in Michigan from 2019 to 2021. So specifically, we're looking at the Detroit airport, which has this airport code, the Lansing airport, Grand Rapids, and Flint. These are the 4 largest airports in Michigan. And this data that we're going to be looking at was scraped using the Any Flights R package. This is a really cool R package. It has records of all flights in the United States, I believe dating back to 2010, along with, so all departing flights among all major airports, weather information like precipitation, wind speed, temperature as well at those airports at that time, delay information, so how much the plane was delayed in leaving or arriving, different information about the plane itself. It's a really rich data set with a lot of interesting things to look at. So here's a picture of the Grand Rapids airport, the closest airport to Grand Valley in this data set. So here's some descriptions of some of the variables here. We're not going to be looking at the weather ones too much in this data set. So these are all, starting here, these are all weather variables. Same with these ones. We're not going to be looking at these in this activity, but we will be looking at the origin, which is the airport, or in this case, it calls it weather station, that the flight was departing out of. We'll look at a little bit the distance of the flight in miles, so how far that flight had to travel, its departure delay in minutes, with negative times meaning that the plane left early, and arrival delays in minutes, which is when the plane arrived before. If it's negative, this means the plane arrived before its scheduled arrival time. You can imagine arriving early is probably more common than departing early, because you can only depart so early. You can't leave without people. Okay. So first thing we're going to do, like usual, is load some packages that we'll need. Okay, so the tidyverse, lubridate, knitr, and skimr packages. So we're going to open up a new R Markdown file. First, let's all right. So you may need to install some of these, hopefully not. And then we should be able to run it. We get some warnings. We'll suppress warnings from like loading packages and stuff as a reminder by adding in the global chunk options message equals false and warning equals false. Okay. And now if we knit that, okay, we can see that there's no warnings. It just loads the packages like we want. So a quick thing sort of as an aside for R Markdown, when knitting to HTML, the default template here is fine, but showing some more options that are available. It may be the case that you want your code to be included in the document, but not necessarily shown. And we can do that using what's called code folding. So this is only an option when knitting to HTML, and it's entirely optional. So if you're knitting to Word or PDF, you can ignore this. But for those who want to knit to HTML, an option using what's called code folding is right here. So you can copy this and replace the output part of the document here. Okay. And if we knit this, we knit this, what you'll see now is there's this cool option that you can hide or show your code. And this will do this for every code chunk in the document. And then you can do it at the chunk level, like hide or show individual chunks, or you can do it for the entire document. So that's kind of a fun thing. Again, only available when you're knitting to HTML. And then one other small thing to show, we've seen the Pretty Docs package is another package that you can use to style your R Markdown template. There's another one called RMD formats. Okay. RMD formats, and copy like this, works with code folding, but unfortunately the Pretty Docs package for styling R Markdown documents does not work with code folding. So if you try to do the code folding, it'll only work with R Markdown, RMD formats, or just not having any template at all. Okay. So I think, let me see if this works. Oh. Let's try that. Oh. Oh, okay, let's see. Let's try that. Maybe that'll. No. Oh, no package called RMD formats. Okay. So yeah, I need to install this package. So installing that, or you can do that by running install.packages RMD formats. And then running that in the console. Okay, you may need to do that. And then that was the problem here, I think. Oh gosh, okay. There we go. Okay. So here's this example template that is the material template, and I'm using code folding with it. So we can hide or show the code. All right. And again, entirely optional, only available if you're using HTML. If you're knitting to PDF or Word, this is not available. Okay. So we loaded the packages. Next, let's download the data file, okay, which is decently large. So you'll have to be logged into your Grand Valley account to access this, your Grand Valley Gmail account. Download the file, which is about 100 megabytes. It's decently big. It's 1/10 of a gig. And if you're working in our Studio Workbench, you'll need to upload this file before we can import it into R. Otherwise, if you're working on your own laptop with R, not our Studio Workbench, you can import this file that we just downloaded now. So to upload a file to our Studio Workbench, you click Upload here, choose the file, look at your downloads, and upload that. And that'll take a bit. So this upload button is only available in RStudio Workbench. Again, if you're working in an R session locally on your laptop, which may be the case, you don't need to do this step of uploading it. You can just import the data set, say using the import wizard right away. So I would, after you download the file, if you're working on your own laptop, I would move the file to the same directory or folder that your R Markdown document is in. That will just make it a little bit easier to import the data if you're having trouble with it. If you're comfortable with importing the data directly from your downloads folder, then that's fine too. Just sometimes it can make it easier to put the data file, the CSV file, right in the same folder as your RMD file is in, and that can simplify importing things a bit. All right, so you can see it's a decently large file, takes a little bit to upload. Maybe I'll pause the video while it's doing that. Okay, so it's finished uploading to RStudio Workbench here. So now we can see the file right here. So next, we import the data into R. Okay, so this step, we have to be a little bit careful about how we're importing it into R, or else we might run into errors with the file path. So one way we can import the data is to use the import wizard. So if we go File, Import Dataset, we'll do from text read R. Browse, navigate to the data file we just uploaded, the CSV here, or that you downloaded onto your laptop. Should be like this. And then we can copy this code from the import wizard and make sure it looks good, and then paste it into here. Again, noting some potential issues you might run into. There's no additional file path besides just the file name here, because this is in the same folder or directory as my R Markdown file is. Data transform main. Okay, that's right here. So here's the R Markdown file that I'm working in. It's in the same folder as the data set. So that's why the import wizard just was able to do this. All right, so we'll change the name because we'll call it MI Flights. Right. Run that. Shouldn't take too long to import. You'll get some messages like this. Okay, and then you should be able to see it in your environment up here. All right. So now we'll use the skim and glimpse functions to explore characteristics of the data set here. So we'll say like, this was importing data, or loading packages and importing data. And then down here, we're doing exploratory data analysis. So using glimpse, we'll take a look at the data set here. And then we'll also use skim from the skim R package. Now, if we knit, okay, open this up here. All right, so we can hide all the code if we want. which is kind of nice. Or we can show it all. So here we imported the packages, imported the data set into R, and then here's the output from Glimpse. So we can see lots of double variables, lots of numeric variables, some character scattered in here. Okay. The output from skim. Okay. You can see that humidity looks pretty unimodal. It gives the histograms for these, airtime, so how long the flight was in the air. It's very right skewed. Number of seats on a plane, also very right skewed here. Okay. Lots of variables here. And also looking at missing values. Okay. So how many variables and how many observations are there in this data set? Okay. So we can see there are about 460,000 observations or rows, 37 variables or columns. Notable patterns of missingness. Okay. So skim is really helpful for looking at missingness. Here we can see, let's see, some characteristics of the planes, the plane manufacturer, model, and engine type were missing. So about 11,000 missing values there. Although looking at the complete rate, 98% of those values were non-missing. So that's actually not too bad. Okay, it's just a really big data set. So there's inevitably some missing values. Let's see, what was missing the most though? Okay, it looks like in terms of n missing, the variable with the most missing values is the humidity. Only 5% of the values. Oh, wait, no. Oh, pressure. Let's see, yeah. Pressure had only 4% of its values there. It had the most missing values. And then the temperature, dew point, humidity, also 95% of the time that value was missing, we can see. So we're not looking at the weather variables in this analysis, but it appears that a lot of the weather information is missing. Although they do have wind speed and wind gust, those values are nearly all always there. So this is a good example of like, if we were trying to fit a model to say, predict the flight delay, these variables are like missing so many values that it's probably can't be used in the model really. There's just too much missing data for those variables. But these other ones certainly could be used. Right. So a little bit of an open-ended question there, but certainly some common themes among the weather variables. Okay, create a bar chart showing how many flights departed out of each airport using the count and geom call functions. Let's start a new section for bar chart. So we're going to pipe mi flights into Ggplot, then use the aesthetics function. We'll specify potentially an X aesthetic and Y aesthetic, or just one of them. Sometimes you only need one for Ggplot objects. So here, instead of using geom bar to make a bar chart, we can use the count function along with the geom call function. So to do that, what we're going to do, and we're trying to make a bar chart where the height of each bar is based on the origin variable, how many times flights went out of a given airport. So we'll do count like this, and then origin. So you can see here what this produces if you paste this part into the console. This produces a frequency table showing the number of flights that went out of each airport. So the count function is great for getting frequency tables like that are tidy, in that there's variables and observations in the data set. Now in Ggplot, we can use a frequency table like this to make a bar chart using geom call. So we'll add a geom call layer. And then thinking about a bar chart, the X aesthetic or the horizontal axis, the X aesthetic is going to be our horizontal axis. So in this case, the origin variable specifies our X aesthetic. And then what determines the height of the bars? Well, the number of flights is what's determining the height of the bars. So in this case, the N variable is how we specify the Y aesthetic here. So if you run that, you should see this initial bar chart here, okay, where you have the different airports and then the number of flights that went out of each. So we can see Detroit, DTW, far more flights than all the other major airports, even combined. Okay. So let's clean this up a little bit. Okay. So first off, sort the bars by descending height using the factor reorder function. So around origin, we'll do factor reorder. And then, so it's saying reorder the factor origin based on the variable N. So if we run that, it sorts the bars by default from smallest to tallest. If you want it tallest to shortest, which is more common, you can sort of trick factor reorder with a negative sign. Okay. All right. Let's see. Okay, so now we'll clean up these labels a little bit, give this plot a title, fix the axis labels, maybe a caption. Okay. So we'll do that using a labs layer. So the title, the x-axis label, the y-axis label, and then maybe a caption. Okay. So for the title, we'll say departing flights. We'll say Michigan, departing flights 2019 through 2021. X-axis, we'll say airport. Y-axis, we'll say number of flights. And for the caption, it's common to make this a description of where the data is from. We can say data source, any flights, our package. All right. Yeah, now it's a much better, more informative plot here. Then we can also add a custom theme onto this. So my personal favorite is the black and white theme, theme_BW, so we'll add that. Yeah, that looks kind of nice. You could add color here. You could fill the bars. As we've discussed before, generally you don't want to add multiple colors to this because it's not adding additional information about which bar is for which airport. That's already labeled here. But you could, like let's say I'm presenting this at Grand Valley somewhere and I want to make these bars blue because it's Grand Valley's colors. So we could manually specify that in geom call using the fill aesthetic. So we could say fill equals, and then I like this color, Dodger blue, a nice little blue. Notice that there's no outline of the bars in terms of color. If you want the outline of the bars to change, fill controls the inside of the bar color. The outside is controlled by the color aesthetic. So typically I like to make that black, like have a black outline of the bars. But it's your personal preference. All right. So that was just a little side detour into Ggplot again. Okay. But moving on into more Dplyr here. Okay. So some important things to keep in mind when working with variables in Dplyr, using Dplyr, is that we'll encounter many different types of variables, some of which you're likely already familiar with. So int is for integers, an example of a numeric type variable. dbl is for double, another example of a numeric type, but integers have to be whole numbers. chr stands for character, which is a character or string value. This is very general, can be like the name of the airport, things like that. A new type of variable that was in this data set. So if you looked at the output from Glimpse and Skim, you may have noticed a new type of variable that you might not be already familiar with. So I have the code here. This DTTM, this stands for date time. So this variable has the value of the date, and it also gives the time of day. And this is when the flight departed. Okay, so DTTM behaves, I would say, more like a numeric variable. You can do addition and subtraction with them, but they are a bit different in their own way. Takes a little bit more specialized functions to work with date time variables well. And so we'll actually look at that in a later video, how we can use the lubridate package to work with these types of variables. But we'll save that for another day. So, but yeah, that's DTTM. LGL is for logical, so true, false valued variables, also sometimes called Boolean variables. And then factors in R are very similar to character values, except there's sort of a specific case of character values in which we have repeated categories showing up over and over again. So in this case, like the origin of the flight, the airport it came out of is a factor variable because many planes came out of each of the airports. It's not like a unique, like if there is a unique flight ID for every single flight in this data set, that would not be a factor. Typically you make factors. Like I mentioned, something that uniquely shows up over and over again, like plane manufacturer. That's another example of a factor. Because you have Boeing showing up multiple times, Airbus showing up multiple times. Okay. All right. So moving on from the variable types there, again, in this activity, we're going to be looking at filter. So if this is the original data set we're working with, filter here is visualized by showing how the original data set, which has 3 rows and 3 columns, okay, filter removes rows potentially based on some logical condition. select can remove, in this case, it removed this last orange column. Select can remove columns from your data set. Mutate can add columns. So it added this yellow column here in the end. And then summarize can condense your whole data set into summary statistics, commonly based on subgroups in the data. And summarize is usually used in tandem with group by to do that for subgroups, although you can summarize the entire data set to get summary statistics just for the whole thing. So all of these functions available in Dplyr are already available in base R without loading additional packages in some form or another. Okay. So there are functions in base R for subsetting by rows. There's functions for sorting things in base R, for subsetting by columns. There's ways to create new columns in base R. All of these things are available without the Dplyr package at all. So what's the benefit? Well, Dplyr unifies all these functions with a consistent structure and syntax. So all of these functions take a data frame as their first argument. The later arguments in each function will be further ways to customize what the function is doing. The reason that's helpful is that pipes, these operators that we use in R, pipe an argument on the left into the first argument of the function on its right side. So because of that, functions that take a data set as their first argument can be chained together to iteratively, or sequentially, I should say, apply functions using the pipe operator. Okay. So for example, I can take the number 5.75 and I'll say round that. Okay. So the pipe operator takes what's to the left, puts it as the first argument to the function on the right. Okay. And that's fine. I could have just wrote like this. So what's the benefit of using the pipe? Well, let's say I wanted to do this, like round, and then let's see another function I can do. Maybe I want to concatenate this with is my favorite number. Okay. Now I get this number, I round it, and then I paste it to is my favorite number. So 6 is my favorite number. Not really true. My favorite number is 8. So I guess change this. There we go. So again, equivalently, I could write like this. And that gives the same result. This is just a little bit more difficult to read than this, which sort of reads as take 7.75, apply the round function, then the result of that, apply pasting to it, blank is my favorite number. So the pipes allow us to chain multiple function calls together in a way that's more readable rather than layering the functions around each other, which can become very difficult to read as you apply 3, 4, or even as many as like 10 functions at once. It's easier to read the chain of the calls than layers of them. So that's the benefit of using the pipe here. And Dplyr plays very nicely in that way with allowing to chain function calls, whereas the base R functions, implementations of these types of things cannot be chained they can't be chained using pipes. There's also other benefits, but I think that's the main one. Okay, so filter. So filter allows us to subset by the rows of a data set. So let's practice by first subsetting to all flights on January 1st in this data set, creating an object called JanFlights. Okay, so the filter function. Okay, so JanFlights, we will say mi flights filter. And then if we look at the variables in mi flights, we have month and day. So we want to filter where month equals 1. Here you have 2 equal signs, and then day equals 1. You run that. See up here, there's about 1,000 observations. All of the month values are 1. All of the day values are 1. So that ran properly. Now suppose we want to create a data set called December 25th. Okay, so maybe try that before looking at how I do that. We can create December 25th. All right, so let's try that here. So month equals 12 for December, day equals 25. All right, so which one had more flights? Christmas Day or New Year's Day? So New Year's Day had the edge, right? Had 1,037 flights and 906 on Christmas Day. Very similar, very close. All right, so the double equal sign we used to check equality here. And this is creating a logical vector here in R that filter is using to evaluate whether or not to keep the rows in the data set. And then we can have multiple conditions separated by a comma inside filter. This acts like an and. It needs both of these things to be true. Month needs to be equal to 1 and day needs to be equal to 1 in order to retain that observation via filter. Yeah. So the double equals is one example of a way we can create a logical condition in filter, but there's many others. So sometimes we want, equals is for checking equality. Sometimes we want to retain an observation if one thing is true or if another thing is true. So just at least one of them is true, essentially. We can do that using this pipe operator, it's called, or pipe symbol. Not to be confused with this is the pipe operator, I guess. And this one we would call the pipe symbol. So the pipe symbol is right above the enter key on your keyboard and serves as an OR for logical expressions in R. The ampersand serves as an AND for logical expressions in R. So if you need two things to both be true or multiple things to simultaneously be true in order to keep that row, for example, in filter, we can use an ampersand. Double equals we've seen. You can check numeric values with greater than, less than, greater than or equal to, which is both of these symbols just together. There's not a single symbol for greater than or equal to in R, and then less than or equal to. So let's see. Let's find all flights that departed in November or December, creating an object called no_DEC. So the or part. So all flights in November or December. Emphasis on the or. So let's copy this. So we'll say month equals 12. So we have month equals 11, or, so November, or month equals 12, December. So that has 79,000 rows. Okay, and if we look at the month, it's all November. There's some December in here. It looks like that worked. So that's how we can do the or operator. Notice if you did, again, the comma, that's like an ampersand, so you won't get anything because there's no flights that left in November and also left at the same time in December. It's not possible. They had to only leave at one time. So important to distinguish between the two here. So this works okay since we only had 2 months, but let's say there is like 6 months. We could do then or month, equals 2 or and so on. That would get to be a lot to type out. And sometimes there's far too many categories to even type out. So what we can use is what's called the in operator. So we'll do equivalent code. Seeing that, and then this one will be using in. Okay, so month in, and then we make a vector of values that it could be in. Okay, so 11 and 12. That produces the same thing. Alternatively, instead of 11 and 12, like this, you can write vectors in R as like 11:12. That produces the same result. If you had like a long sequence of numbers. Okay. All right. So that's some about those logical operations. An important thing to keep in mind here, fix this up a little bit. I don't like how Google's displaying that. So a tricky thing with logical expressions, as you get into more complicated ones, is negation. Okay. So De Morgan's laws tells us 2 rules about negation, 2 equations that are true. So let's say we have 2 logical events, A and B. So A is either true or false, B is either true or false. And by De Morgan's law, the opposite or the negation of A or B being true is either not A, it is equal to not A and not B. Okay. So not A or B is equal to not A and not B. That's the first of De Morgan's laws. The next one, not of A and B, is equal to not A or not B. And I tried to use parentheses very liberally here to make this more clear. So not A is the negation of A, which means that if A is true, then not A is equal to false. And if A is false, then not A is equal to true. Ampersand is what we call the intersection operator. It's, again, just like R here, functioning as an and between the 2 logical expressions. or values. And this pipe symbol is serving as an or sometimes called a union operator. All right. So we'll select all flights except those that left in November or December using this negation operator. So how we can use that, we'll do it with the in operator. So all flights that did not depart in November or December. Okay. So how we can do that, exclamation point, and we enclose the whole expression in parentheses. Okay. It negates the whole thing, and so this we'll call like not November, December. So you can see there's about 385,000 flights. That's a lot of flights, not in November or December. All right, thinking about some other ways we can use the negation here. If, for example, you have this code, let's think about what this does for a moment. What flights will be returned from this top line of code here? Okay, so this is De Morgan's law in action here. So this is an event or a different event. So it's referring to this, and then the whole thing is negated. So by De Morgan's law, it's saying not A and not B. So let's look at the expression on the inside. This one's analogous to A. This is saying the arrival delay is bigger than 2 hours. So the plane was more than 2 hours late arriving. That's A. This one says the plane was more than 2 hours late departing. So these are all very late flights. They were either collectively this on the inside, all flights that were either 2 hours late in leaving or 2 hours late in arriving. De Morgan's law says the resulting thing, because it's all negated, it's going to be flights that were not 2 hours late arriving and not 2 hours or more late departing. So what's another way to write that? Well, this equation right here. So the arrivals not more than 2 hours late, and because it's a comma, that's like an and, the departure delay was not exceeding 2 hours. So these actually produce the same data sets. So that's one way to sort of, that's a little bit confusing. You can think about looking at these equations, how they're, at these expressions, how they're equivalent. All right. So moving on from logical operators here in the filter function, let's talk about missing values for a little bit. So missing values in R are represented using NA and are an important consideration when we try to filter things out or when we're creating logical expressions very generally. It's an important consideration. So let's think about, before we run this in R, let's think about what each of these 4 values would be. A missing value, is it greater than 5? Is 10 equals to a missing value? What is a missing value plus 10? And what is a missing value divided by 2? Well, all these things end up being the same value. You paste these into the R console, They're all missing. Is something greater than 5? We don't know. Is 10 equal to some number? We don't know for sure. It's also missing. What's some number plus 10? Well, we don't know what the result is. And then finally, what's some number divided by 2? All of them, we don't know. What about this next part? NA, is that equal to NA? Let's think about what that will return. If you check this, you may be surprised to see it's not true. Okay, so 1 equals 1 is true. NA equals NA. NA. Why is this? So Hadley-Wickham gives this example of why R functions this way. So X, let's say that's Mary's age. We don't know how old she is. Y is John's age. We don't know how old he is. Are they the same age? Are their ages equal? Well, we don't know because we don't know how old either of them are. Okay, one could be 10, one could be 30. So that's why NA equals NA returns missing value. So how can we check? Because it may be the case we want to check, is something missing? Okay, we have to use the is.na function. So if you paste this into the R console, that's how we can return true when something is missing. So we don't use the equal sign, we use the is.na function. And that's how we do that inside filter as well, if we want to filter out observations that are NA for a particular variable. So let's do that. Let's create a data set called MI flights complete, where all of the departure times are non-missing. So we want to remove observations where it's missing. So create a new section called missing values. Okay. So we're going to filter. And then let's see, what's the departure times variable? Dep time. We want to filter. So if we do is.na, what will this return? This will return all the flights where the departure delay is missing. So how can we get it where they're non-missing? Well, that's where we have to use the negation operator. Let's do not. We run that. Now we can see all the departure times are there, the departure delays. I'm sorry, was it delays or time? Departure times. And then, like we saw, we can keep flights where the departure times are missing by getting rid of that negation. And then we'll call this MI flights miss. So there's 9,000 observations where the departure time is missing. We might want to look at why or what's consistent about all these flights where the departure time is missing. Like maybe it's a particular airport or a particular carrier that is always missing their flight times. You know, that might be an interesting thing to look into. All right, so that was missing values. Now we will look at using the arrange function a bit here. Let's make a new section. All right. So the arrange function works similarly to filter, except it allows us to just reorder or sort the rows of a data set based on a variable. So let's sort MI flights based on the day of the flight from smallest to largest. And then we'll print the first 4 columns and first five rows using the slice head function and select function. So note that when we apply the arrange function, it doesn't alter, like we're going to apply it to the MI flights object. It does not alter the object in the environment here unless we overwrite it. So, for example, here, we go arrange, and we're sorting by the day. Yeah, I can run that. It has all the smallest days first. Okay. But if we look at MI flights itself, well, it happened to be, but let's see. So let's see, yeah, if we did it descending, okay, this would give us like the largest days first. 31, yeah. Okay, it did it when it printed it out here, like the arrange sorted the rows, but it didn't modify the MI flights object. So if we look at that, even though we applied arrange in this way, you can see the days at the top of the object are still the smallest ones. It was unaffected. If you wanted to alter the object itself, you have to overwrite it like this with this code. This would alter the actual object. So if we looked at it, now it's sorted the rows. And sometimes you don't want to overwrite the object. You just want to arrange it and then do other things to the object. So like in this case, yeah, we're not going to worry about it. So day, the smallest to largest, print the first 4 columns. So to get the first 4 columns, we can use select, and then we'll say 1:4. That's how we can get the first 4 columns. And then we can use slice underscore head to get the first n rows, where we wanted the first 5 rows. N equals 5 in slice head. So it's like taking the head off the data set. Okay. So there's the 5 first observations there. Yeah, so instead we can sort by the largest day to the smallest day. And then we'll do the same thing again. So yeah, we'll say this one was smallest to largest. And we'll copy that code. And then largest to smallest. And then if we do DESC, that's what it gives us, both tables in the preview here. Here's the big days and the 5 small days. All right. So that was sorting by one variable using the arrange function. We can also sort by multiple variables simultaneously. So especially when you have many instances of the same value, like in this case, there's many days that were 1. That happened across several different months and as well as years in the data set. So what we can do is we can sort by the year, then the month. So we arrange all the rows into the years. So say starting with 2019. And then within 2019, we can sort by month. So put all the January flights first, and then we can even sort by day. So putting all of the January 1st flights of 2019 first. Okay, so let's do that. So sorting by year, month, and then day. So we go arrange, and then we say year, month, day. So we separate them by columns or commas. Year, the smallest year, smallest month, smallest day. And alternatively, show you what it would look like with descending, you could do, descending year. So the biggest year first, and then the smallest month. So the biggest year, but then the smallest month, and then you could say the biggest day within that. Any combination that you wanted. Right. So arrange is, useful for sorting the rows of the data set. Okay. So I'll let you try on your own. Sort MI flights to find the 3 most delayed flights, okay, using arrange and slice head. Also, you can find the 3 that left the earliest, so the departure delay being the most negative, using arrange and slice head. Then for this part, filter to Grand Rapids and find the 3 flights that traveled the furthest distance. Okay, distance is a variable in the data set, and that simultaneously arrived in the morning. So maybe pause the video and try these on your own, and then we'll walk through how to do it together here. Okay, so for the first one, so we'll call this you try one. So our MI flights to find the 3 most delayed. Okay, so we want to arrange by descending arrival delay, the most delayed. And then we can use slice underscore head and equals 3. Most delayed. Oof. So here's in minutes the delay for these 3 most delayed flights. These poor people. Gosh, how many minutes is, or how many hours is that? 2,600 minutes. Oh my gosh, 44 hours? That's crazy. Okay. I assume they didn't stay on the plane the whole time. There's no way, right? Okay, so yeah, that would suck to be on that flight. Okay. So the 3 that left earliest, let's keep things positive here. Let's look at the people who left early. So or that was the arrival delay. I guess that's not how long they were stuck on the plane, but oof. Okay, so for departure delays, we want the most negative because the 3 that left the earliest. And an early departure is negative departure times. Let's look at that. Dep delay. Wow. Yeah, some of these flights, that's surprising. Like this one left, so this is saying it left 54 minutes before its scheduled departure. I assume they had everyone on board because that seems really early to leave. unless you had everyone already there, a whole hour almost early. Wow. Okay, but then, yeah, that's how we can do that. Find the fastest, highest speed flights. Okay, so this one's a little bit, going to take a little bit of elbow grease here. Okay, so if we look at our data set, there is not actually a speed variable in here. Oh, yeah, there is this speed variable, I guess, but that's not. This is referring to like this the capability, I think, of the plane, but it also has zeros, so it's not correct. What we want to do here is look at the distance that the plane traveled and then how long it was in the air. That will give us the average speed. Okay, so distance divided by air time. So let's see. So if what do we want here? We want the fastest flights. We'll see. Finding the fastest flights. So we'll arrange, and then it's descending because it's going to be when we want the most. And then to get speed, you can actually do functions of variables inside our range. So speed is distance divided by airtime. So you can sort by functions of variables in your data set like this. So these were the fastest flights. Doesn't tell you what the resulting variable is, but it just sorted the values based on that, the rows. And then lastly, for flights coming out of GR, so we're going to use filter to subset to those. So flights coming out of GR. So flights out of GR, so flights with origin equals GRR. Find the 3 flights that traveled the farthest distance and that arrived the earliest in the morning simultaneously. Okay, so we're going to end up finding the 3. So we know we're going to need slice head equals 3. And then in the middle, we're going to need this arrange. Put everything on its own line here. Okay, so for arrange, the farthest distance, so we want descending distance, and then also earliest in the morning. So R, like that. Okay. So that's those flights. All right, so that was the utry section. Now looking at select function. Okay, so here's a visual of how select works. So let's say our data set had columns A, B, C, and D. We can select just A and C using the select function like this. So let's look at an example doing this where we drop the year and month columns from MI flights, creating a new data set called MI dropped. Okay. So we select function. MI dropped, MI flights. And then we use select like this. We're saying drop the year and month columns. Okay. So how we can drop variables if we did year and then month, what this will do is it selects only those two columns. But that's not what we want to do. We want to drop them. So to drop variables in select, we use a negative sign. Minus year, minus month to say that's what we're dropping. Now you can see it has all the columns except year and month. Those have been dropped. So that works well when we just had the two columns we wanted to drop. Sometimes there's like a whole range of columns, like there might be 10 columns in a row that are all contiguous or touching, and we want to just drop all of them. Rather than having to list them all out, select allows us to drop sets of contiguous columns in an efficient way. So we can drop, for example, all the columns between year and day inclusive from MI flights. Call this MI dropped too. So how we can do that is we use a colon between them. Much like 1 to 5 in R says the numbers 1 through 5, when you use the colon between column names and select, it gets all columns in between that range and then drops them. So we can see, looking at MI flights, between year and month, or year and month. Oh, those are the same. Those are the same. Year and day. Oh, year and day. Okay, yeah. I made a mistake here. It's supposed to be day. Okay, so we're dropping all variables between year and day. So that drops year, month, and day. It'll drop all three of those. Let's see if I did that code right. Okay. So it should have one less column than MI dropped 2. See, I didn't do it right. Need to use a parenthesis around here, I think. Yeah, there we go. Year through day are all gone now. All three of those columns are gone. So it's important to include parentheses when you use a colon in tandem with a negative there. Okay. All right, so we can, yes, selectively keep columns, selectively drop columns. We can also do these other complicated operations with select. The first of these functions with select is starts with. So this allows us to grab all columns, or to keep all columns that start with a particular string, for example, ABC. Alternatively, you could use it to drop all columns that start with a particular string, the variable name of the columns. Similarly, there's an ends with, there's a contains. So these strings have to be either at the start of the variable name, at the end of it, or sometimes it's just like, does it have this particular string anywhere in the variable name at all? It's very common that variable names are named things like var1, var2, var3. So sometimes you want to keep all the variables in that particular range. So the developers of Dplyr wrote this helper function num range that allows you to grab those quite easily, or efficiently with a short amount of code. Okay, and then another commonly used function in select is everything, this helper function. So this grabs all columns in select. This is useful when you're wanting to rearrange the position of columns. Maybe you want the time hour column to be first, airtime to be second, and then have all the other columns in the data set after that, while still keeping all of them. You can do that with this code. Okay, so like, let's copy that and look at what that looks like. So see, it grabbed time hour first, then airtime, and then it grabbed all the other columns in the data set. Okay. And this is equivalent with that. This is without the pipe. So you could equivalent code with the pipe. It's like this. Right. So yeah, again, this is useful for rearranging columns or variables in your data set. So you can pick these two columns, put them in the front, grab all the other variables in the data set, and then drop some variables in the data set. You can do many, many operations at once in just one call to select. So you can look at what this looks like. So see here, we have this day variable, but then if we print this code, it dropped the day variable. It's no longer there. All right, so yeah, let's try another utry section. So utry to. So maybe a same thing again where I'll let you try these and then maybe pause the video if you want to do that, and then we'll look at it together. Okay, so let's start with the first one, create a subset only with variables that end with the word time. So how can we do that? And let's see, I don't think I said what to call it. Yeah, let's call it mi flights time. So we'll say mi flights select ends with time. We run that. Mi flights time only kept the variables that had the ending of their name be time. A very efficient way to grab those columns. Let's see, create a new data frame. Oh, we said to call it time flights. Oops. Well, let's do that. Okay. Create a new data frame called departure info. That only has variables that start with dep. Okay. Starts with and then dep. Okay. Two variables that match that. All right. Create a new data frame called new flights. So new flights. By rearranging the columns of the full mi flights, okay, so that the flight number, the flight, origin, and destination are first, then all the other columns, so everything except tail number. We want to drop that. So tail num. So that's new flights. We look at new flights. Origin, destination, everything else except flight number. Okay. All right. So that was the select function. Now we'll look at the mutate function, which allows us to create new variables, which we specify in this way. We say dataset, mutate dataset, or you can pipe the dataset into mutate, and then new variable equals function of existing variables, typically. So let's add a new section for the mutate function. Guess I haven't knitted this in a while, so maybe we can try to knit it. Okay. So now, yeah, maybe we'll hide all the code. Let's look at the output here. That nice bar chart that we made. Okay. Notice that these are not producing output because when we store code or we run code and then we store it in an R object, it typically, not always, but typically does not produce output. All right, mutate function. Let's see. Create a new variable gain that's an existing function of existing variables. Just like this. So we'll take this code and just copy it. Run that. So we can see the gain variable that we did. So how much time did the flight gain? Like given that it was 5 minutes late, when it left, if it was 5 minutes late in its arrival, that's a gain of 0. If it was 10 minutes late when they left, but they were only 5 minutes late when they arrived, that would be a gain of 5. Yeah. So let's see. Let's create a new variable called speed equal to distance divided by airtime. And then we'll put this in a data set called flight speeds. Flight speeds. And then okay, so we'll take this code and then we'll say speed equals distance divided by airtime. Now we can see that speed variable. I see. Yeah, if we open up speeds over here, flight speeds, you can see that speed variable. And that's miles per minute. So if you multiplied it by 60, that would give you miles per hour. So we can see the fastest flight is also one that left early. That pilot really wanted to get going. Okay. So that was that bullet. Create a plot showing the relationship between the speed and time gain of each flight, adding appropriate axis and title labels. Yeah, so let's think about it. So we have two variables, the speed and the gain of each flight. What would be a good plot to visualize that. So it's two quantitative variables. So let's use a scatter plot. Okay. And let's, this subsets it to only the first 5. So let's keep the whole, not just the first 5 values here. Okay. Keep the whole data set. So we'll get rid of the slice head. Now, well, actually, we can keep this one because this is not altering the actual data set. But okay, so we're going to create a scatter plot of the gain by speed. So we'll pipe this into Ggplot. In this case, there's a clear X and a clear Y. So which one would affect the other more likely? X variables are independent variable. The speed of the flight, that would affect the gain in time. Okay. So let's look at a plot of that. Okay. And there's a lot of points here, so this will take a little bit of time. All right, and there we can see, it looks like the faster the flight went, generally there's a little bit of a trend there. The faster the flight went, the more the gain was. Yeah. But there is this weird like U shape in the data. It almost looks like there's 2 distributions of points living in here. Okay. It's also very dense. This is like difficult to see because there's so many points on top of each other. So how can we make this a little bit easier to visualize? Which aesthetic can we use? So whenever you have a large number of points, the alpha aesthetic is helpful to use. So let's set alpha equals, let's say 0.1. Let's look and see what that looks like. Okay, great. Yeah, that makes it a little bit easier to see the distribution of the points. Not a ton, but a little bit. Next, we'll add color to the plot to display the distance that the flight went. So maybe flights that went further were able to make up more time. Let's see if that's the case. So the color aesthetic will map to the distance of the flight. Let's see what that looks like. Okay, so yes, now this is a helpful instance in which we can map a color of a continuous quantitative variable to the points, and it helps us see a trend in the data. So it looks like flights that were able to make up time by going faster, looks like they had a longer distance to go, which is intuitive. They had more distance to make up time. Whereas even if flights were really fast, if they were short flights, dark colored here, they didn't make up much time no matter how fast or slow they were going, because the flight is just so short. There's not much to be made up. Okay. Let's see. So yeah, let's add some appropriate labels here. It's always good to do. So title, x-axis, y-axis, caption. You can also add a distance in miles is the what we'll label this as. X-axis is the speed. Oops. And that is in miles per minute, which is a little bit weird. So if you wanted to convert it to miles per hour, you could multiply it by 60, like that, just right in Ggplot. And then it can be miles per hour. Let's see the y-axis here. That is gain in terms of minutes. Okay. Michigan flight gains by speed 2019 to 2021. And then the caption, I think we gave a caption for our bar plot way up here. Let's just copy that same caption. Okay. Lots of labels to make here. Okay. Nice. And then we can add a, let's see. Let's add a theme, black and white theme. Okay. And then let's move the legend to the bottom of the plot. I think that might be better here. Don't have to, but legend.position equals bottom. Okay. Yeah. That allows us to see this distribution a little bit more stretched out. Oh, that doesn't look great. I bet if you knit it, it looks a little better here for the plot. Takes a little bit. It's a little scrunched. Yeah, we'll leave it for now. Okay. But yeah, that was an interesting little plot to make there. Let's see. So yeah, that was it for mutate. Now on to the last section here. Group-wise operations with group by and summarize. So this is helpful when you have a full data set here. And let's say you have a grouping variable. In this case, it's variable A in the red. We want to calculate summary statistics for each group of A. So we can group by A, the variable A, and then summarize by calculating some statistic or function of other variables for each level of A, each group, subgroup of A. So in this case, it has 3 subgroups. So after we group by and summarize, we end up with this data frame that has just one value for each of the groups. Okay. So let's copy like this code, for example. So yeah, we'll make this a new section. All right, so we'll just copy this code exactly. And let's see. So here, for example, it's grouping by the year, the month, and the day, and getting the average departure delay. So let's, before we do month and day, here, let's just first look at the year. This gives us the average flight delay for each year. So we can see in 2019, across Michigan flights, there was an average of 10 minutes for the delay, departure delay. 2020, it was a lot faster. It was really good. The average flight delay was only 2 minutes. Then in 2021, got not great again, 7-minute delay. Okay. If we added month, this would give us the average flight delay for every month of each of the years, 2019, 2020, and 2021. So that's going to be a lot more. We can see like January looks, oof, not good, 15-minute delay. You start to get into other months, and they're not as bad as January and February. Looks like, yeah, January and February tend to be bad months for flight delays. Not surprising in Michigan, knowing the weather here. Same here. Yeah, January and February are the worst. Okay. And then we only looked at the first 5. So it doesn't have all the months here, but you could get rid of this to have all the months included. Okay. And then you can also do it by day of the month here. Okay. So that's looking at different dates. Maybe what's more interesting, which carriers, so like Southwest Airlines, Delta, Spirit Airlines, which ones have the worst flight delays on average? So like Spirit Airlines gets a lot of flack for being awful to fly with, right? But are they actually bad in terms of flight delays? They're really bad about getting you with hidden fees, but let's see about flight delays. Okay. So if we use this code, we get the average flight delay for each carrier. And then we will reproduce this bar chart, this special case of a bar chart that's called a waterfall plot, because the height of the bars can be negative, or this is a bar plot, sorry. Special case of a bar plot called a waterfall plot, where we have negative going into positive values. So we're going to use geom_call in this data set that we just created using group by and summarize. So we'll take delay summary, pipe that into Ggplot. And if we look at the activity, what's our x-axis variable here? It's the carrier. So carrier name is our x-axis variable. Our y-axis variable is the delay time. If we look at like this delay summary data set that we're using, we have the carrier, then we have the delay. Then we do geom_call. And yeah, that'll produce a plot here. It'll be a little bit busy, but we're going to fix it up here. So all the bars are not in order of their height. We want to sort them by height. We can use the factor FCT reorder function. And then we'll say by delay. Okay. So that's how we get it like that. Let's see. We can fix up the x-axis, y-axis, and overall title labels. There's actually even a subtitle in this plot here. So X is the what do we call it here? Carrier. Y is the average delay in minutes. Title, average flight delays by carrier. And then the subtitle, which shows up as a little bit smaller font here, just below the title, Michigan flights, comma, 2019 through 2021. Okay. All right, almost there. And then we add a black and white theme. Now it's looking really close. Okay, we're almost there. So changing the inside of the bars here, we want it to be red if the plot, if it's if the delay was negative on average, and we want it to be blue if it was a positive delay. Okay. So red is actually like, let's see. Red is actually good here. Right, because we want a negative delay. We want to be arrival delay. Yeah, we want to be getting in early. So we want our flight to get in early. So the red ones are better here. Blue ones are worse. Like they're getting in late. All their flights are getting in late. Okay. So let's see. Okay, how can we change that coloring? So that is the fill aesthetic, since it's controlling the inside of the bars, the color of that. So inside geom call, we'll specify the fill aesthetic. And we want to be the fill to be dependent on if delay is greater than 0 or not. Let's see. So we're going to say we want fill to be equal to oh, it's delay with a lowercase d. Oops. Okay. Delay with a lowercase d here. State. Oops. There. Oh, let's see. Delay summary, maybe something was wrong in here. Delay. Let's see. Oh, okay. I see the mistake I made. This should not be inside geoncall. It goes inside AES. Okay, so since it's a function of the variables in the data set, it needs to go inside AES. Okay, there we go. And now Ggplot picks these colors by default, which are not great. So we will, since there's only two colors, we could do like a palette, but we want this to be like specifically blue and red. So we can do that using, since this is the fill aesthetic, we can do that using scale fill manual. This is useful when you want to manually specify, like, I want this color in particular for each group. And then we say values equals, and then we're going to do a vector of color names. So I'm going to use what's called the hex codes for those two colors. These are two special colors that are colorblind friendly, like blue and red, essentially. Okay. So it's not exactly just plain old red and blue. All right, so that's how it looks. We don't want this legend here, so we're going to add theme legend dot position equals none. Okay, boom, got rid of that legend. Okay, we're getting there. Yeah, we're really close. All of the font in here is bold to make it a little bit easier to see. So we'll change that in the theme as well. So we'll say text equals element underscore text base equals bold. Okay, that'll bold all the font in the plot. There we go. And then now we have this issue of like all of the carrier names overlapping, right? So how can we get around that? Well, one thing we can do, it's not the only option, but one thing we can do is angle the text on the x-axis. So also in theme, we will specify axis dot text dot x, since it's the x-axis, equals element text, and then we say angle equals 45. And now let's knit this and see what that looks like. Okay. Takes a little bit. What we're going to see is that it angles the names of the carriers, but there's some spacing that still gets messed up a little bit in the x-axis labels. So we'll fix that. Okay. So see how the names of the carriers are so long that they get written on the plot? That's not great. So we can push them down, push the labels down vertically. So how we can do that is inside this axis.text.x, inside element text, we can say, for one, size equals 8, we'll reduce the font size of the x-axis text. And then we'll say vjust, which is for like vertical adjustment, 0.7. And if we knit that, takes a little bit to knit. But hoping should look good now for the x-axis here. There we go. So that's how we could bump it down a little bit so that it's not overriding onto the plot. Okay. So there's our final plot. It doesn't look exactly the same just because the dimensions can get a little bit messed up depending on which computer, or like this was made by knitting to Word, so it's a little bit different than knitting to HTML. But yeah, so this is the flight delays, average flight delays for all flights in Michigan by carrier from 2019 to 2021. So we can see Endeavor Air and Southwest had the best outcomes in terms of they left early, typically. They didn't leave late, at least on average. Delta, also really good. Alaska Airlines, also really good. American Airlines. Spirit, this is where I like to point out, like, yes, they were worse than the other ones, but hey, they weren't too bad. You know, they weren't too late. If you're looking at who's bad, look at Allegiant Air here. Oh gosh. They on average left almost 15 minutes late. That's awful. JetBlue, not great. I haven't heard of Express Jet Airlines LLC, but gosh, I wouldn't fly them. They look like they're late a lot. Okay. Not good if you have a connecting flight. So yeah, so we were able to reproduce that plot. Here's some more try on your own. So summarize the median flight delay by month. Which month has the worst delays? Which month's flights most early on time? Okay. So yeah, this is like a you try number 3. Last one. Okay, so we'll get the median flight delay by month. So we'll say like, yeah, month delay summary, or monthly delays, something like that. And then group by month instead of carrier. And then instead of mean arrival delay, we'll do median. And then we don't need this option NA remove equals true. I don't think that's, let's look at the help file for median. Oh, no, yeah, we can do that. Okay, NA remove equals true. We'll keep that. All right, that removes missing values. Otherwise, if you have like the median of the vector 1, 2, NA 4, 5, makes that NA. But if you do NA.rm equals true, it'll still calculate the median just with the values it has. So since there's missing values in this data set, we want to do NA remove equals true. There's monthly delays. We can print that. Maybe make it look nice using knit or cable. So across 2019 through 2021, looks like January Yeah, okay, so the median is very different than the mean, which is interesting. So half of all flights got in early. At least. All of these negative arrival delays for the median means that half of flights got in early or on time. It's great. So for January, flights got in the most early. Flights that were the worst would be June. But even then, the median is negative, which is good. Which type of plot? Okay. So given this, it's time series data, so a line chart is always helpful here. Okay, so let's make a line chart. So creating a line chart. using Ggplot 2. Okay, so monthly delays. So we'll pipe this into Ggplot. So our x-axis for the line chart is going to be month. The y-axis will be the delay, which is the median delay for that month. And then we'll do, to make a line chart, it's geom line. Okay. That shows the median flight delays across the year. Let's see. We can add a theme, make it look a little nicer, add some labels. We'll say monthly arrival delays. And then maybe the subtitle. Michigan flights 2019 through 2021. Caption. Make the same as this one. Caption, and then the x-axis and y-axis labels, gotta have those. So for the x-axis, it'll be month, and then y-axis, it will be median delay in minutes. Let's take a look at that. Here we go. And then, so the months, yeah, it's like it's the numbers 1 through 12. So R is like, oh yeah, it makes sense to put half on here. But really months is like discrete. You can't have like, yeah, I mean, these intervals are all at the whole month value. So there's a few ways you could fix this up. Let's see. I think if you do this, yeah, okay. So we can use this function from lubridate, the month function. So what we'll do is we'll say x equals month. So like this, around this, this is a little bit of a hack, but let's see if that works. Yeah, cool. Oh, no, it lost the data. Shoot. That won't work. Let's just leave it as this then, and then we'll do, if we want to force the breaks at certain points on the y-axis, you can use scale x continuous, and then you say breaks equals, and then we'll say like 1 to 12. Let's see how that looks. That's going to force breaks at each whole number 1 to 12. Yeah, that looks fine. Okay, cool. So that's our cool line chart. Let's say you like, again, wanted this line to be blue rather than black. In geom line, you could do color equals Dodger blue. A little more fun to look at. Yeah. So this kind of shows how you can see, yeah, it looks like delays get progressively worse, peaking in June, and then starts to get better again until it gets bad in October for some reason. That's kind of weird. Yeah, that's what happened though across all the flights. So I guess maybe like people flying for Thanksgiving or something, end of October. Yeah, that's a little surprising. Not sure why that would be the case. Facet by where the flight departed from. You will need to use group by again to do this. What are your observations? Okay. Yeah, so let's copy this chunk like completely. Okay. And then we're going to use group by. So we also want to group by origin. So we're adding that in here, and we'll call it like monthly airport delays now. Make sure you update monthly delays to monthly airport delays in each of those spots. Add origin. Okay. And then what we're going to do is facet by the origin. Okay, so we're still going to keep all this code the same for the Ggplot, except we're going to add a facet underscore grid layer where we let's see. Let's think about how we want to do this. Facet.by. You know what? Let's try just the facet function, and then we'll say facet.by equals origin. Let's see if that works. No, I didn't like that. Okay. Well, yeah, we'll just do facet grid, and then let's do origin tilde grid like this. See how that looks. It doesn't really facilitate comparing across the airports, but probably the best way to view that. Pass it by the, what are your observations? You know what? Sometimes a facet is helpful. In this case, I think it's better to keep them in the same plot. So like, yeah, here's how you do facet it. We'll look at the results here in the knitted document. Yeah, so it is kind of helpful. I guess you can see a little bit of the trends together, but I almost think it'd be better to color the lines by the origin. So let's try that real quick. So can facet it here, but let's try coloring. Yeah, we'll take out color equals blue and then add in AES. We'll say color equals origin. Okay. And then take out the facet grid. So we added color equals origin inside AES. We took out the color blue from geom_line, and we took out the facet grid down here. If you run that, yeah, now you can see this makes it a little bit easier to compare across the airports. So we can see like Flint is looking like it tends to have the worst median delays. Whereas, yeah, who's in purple? That seems to be the best. Lansing. Oh, yeah, Lansing. It's a really small airport, I guess. Seems to have the best outcomes in terms of delays, followed by Detroit, maybe, or Grand Rapids. It's kind of between those two. Okay. All right, but you could keep the facet as well, up to you. And then, yeah, you could do a similar plot, but looking at the mean instead of the median. You would probably see very different results because the median, this is going to be very skewed, the departure times or the departure delays. So, or sorry, arrival delays. So you might see a different trend here. It'd be interesting to see. So that's optional. So that's it for this activity. So that's some fundamental functions of Dplyr that help us with data cleaning and wrangling of our data.